All right, welcome. This is day 9 of 30 days of machine learning. And today, what do we have on our hands? We have the same problem uh, that we had on day 8, which was insurance expense prediction. And, basically, if I go back to the board to show it to you, we deep dive in the ensemble learning concepts, explaining everything. And we chose the gradient boosting model as our current model in order to implement this. This is what we chose on day 8. And, everything is explained. So you are very welcome to check out the video for day 8 to understand everything from scratch. Then, I explained as to why, XGBoost is chosen over gradient boost models usually, which is why, we are implementing it from scratch in day 9. So, XGBoost it's the best. It's the GOAT. It's the daddy of all daddies. It's the best boosting model to exist out there. Now, in general, there is nothing such as the best because it all depends on what trade-offs and what situation, what kind of problem and what kind of data set we are dealing with. But, if you are given a tabular data set and non-linear relationships, and you have, the tabular data set size less than 10 million, okay, which means like a medium to large sort of a data set, you will implement XGBoost as it is the best choice to implement in that moment. If it goes beyond 10 million samples, we will have to definitely go for somewhat of a deep learning based solution because, capturing these many non-linear relationships is a very difficult task. But before that, it will handle the model the XGBoost model will handle capturing the relationships very elegantly. Okay. It is one of the most mathematically sound models to ever exist. Okay. I get dreams of XGBoost. It's amazing. And we since we are implementing the same problem, the EDA, the data processing pipeline, and all of the implementations that we did on day 8 are exactly the same. But what's going to change is the most important part of the video, which we are immediately going to start with. It is nothing but the model physics of XGBoost. Okay. So if I scroll down, we did discuss the physics of gradient boost, how it works, and we discussed it end to end. This is how the model trains residuals and everything. Then we discussed the intuition of the gradient, what it does, how we make the updates, and then we eventually discussed the time and space complexity as well. Okay. So similarly, we'll be discussing the entire physics of XGBoost today, and it is quite large in number if we are considering the number of steps, but it is very interesting, and it basically forms the basis for why XGBoost is such a strong model. Okay, so I will be discussing everything end to end from scratch. So, just hear me out very carefully. First of all, let me go to the repo. I will attach the link to the repo in the description. And one thing that I just wanted to remind you for day 8, day 8, we covered ensemble learning as a very important part. And I basically introduced the 5 types of ensemble learning, the 5 methods using which we can implement it. It is these 5: bagging, boosting, voting, stacking, and blending. Out of which bagging and boosting are the most popular ones. Voting, stacking, and blending, they're not covered anywhere as popularly as the other two. So what I have done is that on the day 8 video itself, I have attached a link in the description which consists a very detailed article about all 5 of them. So if you are curious and you want to, study about them, you can go and check out that article, read it. It is very simple, a very nicely written article, and it describes all 5 of them very intuitively. Okay. So coming back to today's problem, let me scroll to the bottom. This is our board, okay, where we'll be solving and discussing everything. So this is the problem, okay. The repository is only different for the model physics and the other stuff, but the problem is the same. So you can read it alongside, you can read it later. It's pretty simple. So, XGBoost addresses all of the problems, most of the problems that we were having on day 8. Okay, so as we know that decision trees and even random forest, or basically any ensemble of trees where there is a collection of trees, it is very easy for the tree to overfit, especially if the trees are deep. Okay, so we have to deal with that overfitting problem, and we do that by regularization. Okay, so I'll be discussing how we do that, but right now let's just quickly go through these points. Okay, so we use first order gradient information. I'll discuss what that means. So greedy tree growth, training instability. These are the sort of limitations of the gradient boosting model that we got, which we are going to deal with in the XGBoost. Okay. So you can read this problem statement is the same. This is all from the day 8 repo itself because it's the same problem. It's the correlation heat map. Now comes the main thing, okay, that we'll discuss slowly and very carefully. So let me go back to the board. Okay. Now, pay very close attention. This is all that we are going to discuss for the video. There's nothing else. We are just discussing how or what exactly is XGBoost doing, what makes it so strong. Okay. The derivation, the maths, the intuition, everything. And it's a bit long because there are lots of concepts involved, so pay attention. Okay. So I will start from the beginning. It's pretty simple. So what do we have on our hands? So we have on our hands nothing but boosting kind of ensemble learning implementation. Okay. Boosting means very simple that we take a bunch of weak learners, like a bunch of weak models, and each weak model learns from the errors of the previous one while moving forward. Okay, so it's very intuitive, very simple, and we keep adding weak models until the number of weak models are finished. There's a limit to it, and or if the model converges, which means that the loss function becomes close to zero. Okay, that is how we train any random boosting model. Now, when I write it down for XGBoost, so I have got on my hands XGBoost. Now, XGBoost, what does XG stand for? So when you open it up, the full form is Extreme Gradient Boosting. Okay. So we know what the gradient is. The gradient is basically the slope or the partial derivative of the loss function. Okay. So, now moving on, what is actually happening in the model? Now, this is like a very simple rule to know and to always keep in mind. Eventually, how does a general machine learning model train? How is it trained? How do we move forward while implementing the model? It's a very simple thing, we calculate the loss function. Okay. And the loss function is basically the difference in the values that we predicted and the values which are the actual values. Okay. We subtract them and do some sort of mathematical operation on them to find the loss function. And our job is to reduce that loss function, to minimize that function. Why? Because if the loss function is minimized, it means that our predicted values are very close to the actual ones and the model accuracy is high. The model is a strong predictor. That is what we want. So that is the essence of what we are going to do now. So, first of all, I'd like to discuss as to, how does the loss function of XGBoost look like? Okay, it is not like a regular loss function. If I write, okay, so OBJ function means objective function. It means the same thing as loss function, but I'll just tell you how stuff happens in it. So I've got the objective function on my hands. It is nothing but the sum of the loss function and the regularization. Just a second. Small error. Regularization term. Okay. So, as I discussed just about 2 minutes back, XGBoost is considered as a pretty strong model because the first reason why it is considered strong is because it has automatic regularization in it, which means that, the tree gets pruned. Pruning means, where we chop off some of the nodes of the tree when it is getting too deep. This basically prevents overfitting. Now that this step we usually have to do in a decision tree or a random forest model separately. But that is not the case in XGBoost. When we implement an XGBoost model, the regularization term is inbuilt. The tree gets pruned on its own mathematically. How does that happen? I will show that to you. First, just let's go on forward. Okay. So I've got the objective function on my hands. Now, of course, the question is, this is English. Okay, this is English. What does the regularization term look like? And what does the loss function look like? So let's check it out. The loss function is nothing special. It just is the mean square error. Yeah, no, I'm not kidding. It is that simple. The loss function is nothing but the mean square error, the same mean square error that we use in linear regression problems as well. Okay. So when we write mean square error, we write something like 1 upon n sigma for the summation I is equals to 1 to n. And, we go from yi minus yi hat whole squared. Okay. This is how we write the standard mean square error function for, let's say, linear regression problem. Now, for XGBoost, we make a couple of changes. Okay, very simple changes. So what we do here is that, since a linear regression model only maps linear relationships and it's a singular model, whereas in the case of boosting, in the case of XGBoost, we have got a series of models which are learning from the previous term. So this 1 upon n term does not make any sense because this is just to average all of the results for all of the n predictions that we made. But in XGBoost we don't want that because we are not averaging anything. The newer model is learning from the results from the mistakes of the previous model. So this 1 upon n term is actually not part of the loss function. Okay, so it's like a modified kind of a mean square error. Okay, and one thing which is added, which is pretty simple, it's a mathematical trick. We rather write 1 upon 2 here. And why do we write 1 upon 2? It's pretty simple. So, you should imagine this function. First, imagine this function. This is the mean square error. Okay, this is the loss function. So if I write it as f, so, this is what my loss is looking like. And it's like yi minus yi hat whole square. Now, how do we move forward? We want to minimize any loss function, so we take the derivative, the partial derivative. So we take the partial derivative of f with respect to y, and we get something like 2 multiplied by yi minus yi dash. Okay, just a second, since I don't like these errors. Okay. We get something like this. Now, the thing that happens is this too becomes very irritating to handle because it cannot go anywhere and it just makes the results a little less interpretable. This is very interpretable, this term right here. It's just saying that, we have got the difference between the actual values and the predicted values, which is actually the loss function. But what to do about this too? Now, imagine that in our loss function, rather than this value, we also add half right here. We can, because it's not going to make much of a difference. So when we add this half right here, now, what happens is when we calculate the derivative of the loss function, there is already a half present here. And this two get cancelled. And only this term remains, which is much more easier to handle and much more interpretable. Okay. This is why whenever we write the loss function, we add a half to it and we remove the n because we are not averaging. Okay. So let me write down the loss function again. So what it's going to look like, let's say that I call the loss function as maybe L because, well, let's save some space. There is no point of writing the whole thing again and again. So I will write it as n sigma I is equals to 1 capital L for the loss function, okay, and then then the actual and Wait a second. Then the actual along with the predicted value. Okay. This is how our loss function is going to, look like eventually. Now this is handled. Okay. We understand that this is, our loss function and this is what it's looking like. Okay. Pretty easy to understand, pretty easy to interpret. Now we go on to the regularization term, okay? Because the tree is getting mathematically pruned in itself, so we need to understand as to what the regularization term looks like. So when I write the regularization term, it just looks like L2 regularization. So if you have not studied L2 regularization, I have again added an article regarding L1, L2 regularization and elastic net. It just sounds complicated. It is very simple to understand. They are basically techniques to prevent overfitting in machine learning models. And they're very popular, especially with trees, because trees are like very prone to overfitting. Because, if you're not careful with the N estimators or with the max depth, the tree can overfit like this. We don't want that. Okay. So the regularization term looks something like this: half lambda summation of W J squared. Okay, this is what the regularization term looks like. So don't worry, I will explain what all of the things are. So WJ is nothing but each of the leaf weights. So if we have got J different leaves in the decision tree in the each weak learner model, and each of the leaf has a weight of WJ, then that weight is counted here as WJ. Okay. This half is again added to make it better for calculation purposes. This lambda is a hyperparameter. Okay, hyperparameter. What will it do? So this is very important to discuss. This is one of the hyperparameters here. So lambda here, just a second. Lambda here is the main thing that works. It reduces variance and stabilizes and smoothens our predictions. Okay, okay, simple. How will it do it? So it will be different for different values of lambda. I have discussed this in the repo as well. So if lambda has a value which is zero or close to zero, it will definitely lead to overfitting. Because if lambda is zero, then this whole term becomes zero. If lambda is zero and I put lambda in here, then this whole thing comes out as zero. If this whole thing is coming out as zero, then we basically did nothing because zero is getting added to the model. Nothing is happening. And if this lambda value is too large, okay, if this lambda value is too large, what will happen is that something of a high bias situation will happen and it will lead to underfitting. Okay. If the lambda value is moderate, if it is like a controlled value, then it will lead to much, moderate and generalizable results, the kind of results that we are after. So this is a hyperparameter, and again, we don't write its value manually. We take some logical values and we feed them to grid search CV. It sorts out the parameters, chooses the best combination, and returns the best one with the highest accuracy to us. Okay, so pretty simple. So now, if I write the entire function, so the thing is, this is one part of the regularization term. Okay, this is L2 regularization. So this is one part of the regularization term. If you want me to write it down, I can write it. So this is the L2 regularization part of the regularization term. But there is more to the regularization. There is another term. So the other term for the regularization, let me change it, looks something like this. Gamma multiplied by T subscript leaves. Okay. So I wanted to separate them out and explain it. I will tell you what the resultant looks like, but First of all, let's understand it. So, what is the purpose of this? The purpose of this term, this entire term, okay, is nothing but it penalizes penalizes too many leaves. Okay. What does this mean? So, for to understand this, you need to grasp a very important concept. See, whenever we build a tree-based model, a model where there are initial nodes and then the split is created using ID3 or CART algorithm, and which means either Gini impurity or entropy, information gain. Whenever we create splits using that, we are increasing nodes every second. And whenever we are increasing leaf nodes, what's happening is that the model complexity is increasing every second. Overfitting risk is increasing as well, but the model complexity is rising slowly. So if I show it to you, like in diagrammatic form, let's say that this is the original node, okay? And we split it into two nodes like this. Then again, we create a split for this one. For this one, we again create two more. Then two more for this. Okay. Two more for this, and so on. So you see, this depth of the tree is increasing like by 2 to the power n. Okay. If you want to calculate the height, it will look something like logarithmic to the base 2L. Okay. So this height is increasing by this factor. So the model complexity is rising every step. Even one step can make a huge difference. Okay. So what happens is that when we add too many leaf nodes, so what are leaf nodes? These nodes, okay, the nodes which are not directly attached to the parent, the nodes which are towards the end. These are called as the leaf nodes, the nodes which are at the end. So when there are too many leaf nodes, the model starts becoming complex. So we ask the question, what's that question? We ask the question whether the model complexity is worth it. What does this mean? So we are basically asking that, okay, the model complexity is increasing every step, but do I need that much complexity? Is it actually contributing to my model, or is it just wasting the time and just disrupting the interpretation? How do I check that? I'm checking that using this formula right here. Okay. So tea leaves is counting nothing but the number of leaves that we have in the tree till now. And this parameter, okay, this is the Greek symbol gamma. It is a hyperparameter which basically controls whether or not our split is worth the model complexity. Okay, I will repeat and I will write it down as well. Okay, let me write it down in a new space. So gamma is controlling whether each split is worth increasing the model complexity. Okay. So again, I will like to repeat it because bit this is a bit confusing to grasp. So what we are saying is that with every level, our model complexity is increasing. So we are asking the question that is it worth increasing? When we are increasing the number of splits, is it actually contributing in making the model interpretable, making the model generalizable, making it converge faster, or is it just wasting our time and complicating it too much? We are checking that by the use of this gamma parameter. So what happens is, I will show this to you in the final formula as well. Basically, when we are creating the split, we calculate the gain value using the formula that we calculate, and then we check if the value of gain is greater than this gamma value, then and only then we select the split. So, our end formula looks something like gain minus gamma. Okay, so we ask the question whether this gain is greater than gamma. If it is greater than gamma, it means the model is worth having extra complexity. And we say that, yeah, okay, extra complexity is good here because it is actually helping the model and we can create the split. But if this gain is less than gamma, then it's not worth having all that extra complexity and we basically, ignore it. and we don't take that split. We try to create some other split. That is the intuition here. Okay. So gamma here controls that, and it is again a hyperparameter value. So, we again can give some logical values and then analyze the good value or the appropriate value using grid search CV. Okay. So that is what we do. Now let me combine these two. So I have got two terms for the regularization. I've got, let me change the color quickly. So I have got this term as one of the regularization terms, which is controlling, uh, you know, basically it is for penalizing too many leaves, because if there are many leaves and it is just increasing the complexity, it will penalize it. It will put a penalty on it. And then I have this term, which is basically the L2 regularization term. So if I write them as combined, I can maybe, write them like this. So we have got like, ohm of F, okay, and we have got gamma multiplied by the number of leaves in the tree. We add half and we put lambda, okay, which is the regularization hyperparameter, and the summation of all the leaf weights. So this is what our regularization term looks like. Okay. I'm doing it step by step so that everything is absolutely clear. Okay. Again, I'll write it down. This one penalizes, puts a penalty on what? On too many leaves. Okay. Wait. On doesn't go here. Okay. Yeah. This one penalizes too many leaves. And what about this one? What does this do? It penalizes large outputs. Okay. Because they might cause overfitting. So it puts a penalty on them and reduces them to prevent overfitting. Okay. Penalizes large outputs. Okay. So this is what's happening. Okay. This is what the regularization term looks like. Now, let me jog your memory quickly so that it all makes sense. Now, do you remember this loss function that we have? This loss function right here. Now, what happens is, since I said that the objective function of XGBoost has a loss term, which is this right here, and it has a regularization term. Now, we just calculated the regularization term, which is this. So, what does that make our final formula look like? Let's write it again. So, our final formula, which maybe I can write it as OBJ, which is the objective function. This is the function that we have to minimize or reduce. Why? Because this is the eventual loss function. Okay. It will look like this loss. Okay. Capital L. Okay. And we will add to this nothing but this ohm of s. Okay, this is again another Greek symbol, ohm. I'm not writing ohm completely because we just wrote it above. It's no point in just copying things. Okay, this ohm of f is nothing but this ohm of f right here, the regularization term. Okay, so this is what the final formula becomes. Now, before moving forward, before finally doing the optimization, which means reducing the loss function to its minimum value, we do have to do one more thing. One more thing. It's a very quick optimization, and it's very intuitive to understand as well. So, we have got this loss function right here. But can we move forward with this? No. The answer is no. Why is the answer no? See, because this is basically like an interpretation of the mean square error loss function. But the thing is, the model here is not behaving like a standard model. It is a boosting model, which means that every model is learning from the mistakes of the past model. So, can the loss function look like this? Can it look this simple? No, it cannot. We have to do some changes. What will it look like? So for that, I'll quickly go to like a simple example of boosting. So let's say that I have trees. This is my tree number one with two nodes as a weak learner. Okay. Then tree number two here, the next tree, another weak learner. Tree number three right here, another weak learner. Okay. Let's draw another. We can have as many as possible, but I'm just doing this for an example. Okay, so I've got four trees right here. Okay. And just a second, let me remake it. Okay. So if I write it down quickly, I've got T1, T2, T3, and T4. Okay, I made them small trees because I just want to use them to explain an example. It can be bigger ones as well. Again, depending on what values we have chosen in the code itself. Okay. So what's happening is that this T1 will calculate some value of the loss function. Okay, and it will pass on its predictions to T2. T2 will learn from the mistakes of T1 itself, and it will again calculate its loss function. It will move on to T3. T3 will again calculate its loss function, and it will in turn learn from the mistakes of T2, and it will keep moving forward. And this way we continue until we reach model convergence, which means that the loss function has converge, which means it has reached an ultimate minimum value after which it cannot be minimized more, or these models get completed, which means let's say we have got six allowed models, six allowed weak learners, and all these steps have been completed. So we then stop. So, if we try and write this in mathematical form, let's say that, the output at step one, which means after T1. Let's say that T1 sort of produces an output. Okay. And then we go on to T2. So T2 is learning from the corrections, learning from the mistakes of T1, and it also has predictions of T1. So if I try to write the output of T2, let's say it looks something like, y of I. Okay. And I have just put a cap here to know that this is the calculated value. And this will basically contain the output from T1. So T1 is nothing but yi hat, and I write T minus 1 here. Okay, T minus 1. T minus 1 is just to resemble that we are going a step back because, this is T2 and this is T1. So T1 is exactly one step back from T2. Okay, so we write T minus 1 here. This is not multiplying, this is in the superscript. This is just to signify that we are going a step back. Okay, and then we add to it the corrections that the model learns. And the correction looks like a function ft x of I. Okay. So this is what the output at each step of the XGBoost model looks like. Okay. This is basically the predictions that we get from the previous step. And ftx of I is nothing but the corrections that the model is making. Now, one very important question that anyone will get is that why are we writing the correction here as a function? Okay, why have we not just given a value? So this is very simple, but it's a good doubt because let's say that when we go from T1 to T2, the error, the correction that T2 learned from T1 was like a plus 5. Okay. Then from T2 to T3, T3 learned, let's say, correction of minus 3. T4 learned a correction of plus 12. Do you see my point? The point is the correction at every step between trees is going to be a different value. Okay. The value which is calculated in the tree itself using the loss function. We don't know exactly what value is that. It's not constant value, it's not a fixed value. To model that, we rather just write a function. Okay. This x of I is nothing but the current label, and based on that, it is used as the input in the function ft, and it produces some output which is eventually the correction value. Okay. Now, now, as our final task to create the loss function, we have got this loss function right here. Okay. And what we do is we have got this yi and yi hat here. What we do is we take this yi hat value and we plug this value into this. Okay. So take the yi value and input it in this. Okay. So we input it in this, and then we get something like this. Let me write it down to, make it clear. So it will be like a pretty long term if you want to see it. So, and write it as loss. We write it objective function. Okay, so I get my, yeah, objective function, and it is nothing but loss of y I comma what we calculated right here. Okay, this value. So we input this y I hat t minus 1 plus f t as a function of x of I. Okay, this completes the loss term. And added to that, the regularization, which we, sort of combine and write because we don't want to write that long term again and again. This is a part of this. Okay, so our final loss function, what does it look like? Our final objective function, it looks like this. It's too long. Let me write it here properly. Okay, this is what the final objective function looks like. Okay, right here. This is what it looks like. Okay. Now comes the main task. Okay. Till now we are just playing around with making a loss function. So this is basically how the loss function for XGBoost is made. Okay. This is how the loss function is made. Okay. So now comes the main task. This is the important part. What do we do with the loss function? What do we do with any loss function that we get? We minimize it. So our value now is to optimize or to minimize this entire function. Okay. So our goal is to minimize this entire function. Now, let me tell you something. This function, when we take this and put it through the classic Euclidean space and try to minimize it, if we take the like if we take the gradient or the derivative and we try to minimize it, it comes out as nearly impossible because this is a very complicated function. See, what we have is that we have this value right here, the true label value. Then we have the predicted value at step t minus 1. We have a function for the correction as well. And we have a regularization term. So this becomes too complicated to do with simple gradient steps. So rather in this case, what we do is we go for a second order Taylor approximation. Okay, I repeat myself, a second order Taylor approximation. So again, if you have not heard of a Taylor approximation and you want to understand about it, I have included a link in the description about the article for a Taylor description. It is a part of the Taylor series, which we learn in, I think, in the integral calculus 2 in university itself. So if you have not studied it, it's pretty easy to understand. It's basically a very neat mathematical trick. And why do we implement that? Because it's the most straightforward thing to do here to get like a quadratic function, to get a easier function that we can try and solve further. Okay. So we apply the second order Taylor expansion, and that is where things get interesting. So now, look carefully. So when I apply the second order Taylor approximation, I get something like this. So, I can write loss, and it will look something like summation of from I to n gi f p of x I plus half h I f p x I whole squared. Okay, this value right here. And we add to that our standard, you know, regularization term. It is unaffected right here. This is what our loss function transformed to after doing the second order Taylor expansion of loss. Okay, this is an approximation, so I'll put this sign rather than the equal to. Okay, this is what we do for the approximation. Okay, भाई रिकॉर्ड हो रहा है ना बहुत मेहनत का काम है हाँ ज्यादा नहीं रह गया बस बहुत बढ़िया ओके yeah so this is what we do now don't worry I'll be explaining what each of it means and it is pretty intuitive because this is what drives XGBoost at its core so now if you allow me to write what is g of I g of I is nothing but the gradient del L by del Y hat okay does this look familiar does this look familiar yes it looks familiar because it is nothing but the gradient okay it's nothing but the gradient. Okay. It was being repeated too many times, which is why, instead of writing del L by del Y hat repeatedly here, I just wrote it as G of I so that it becomes, the formula looks cleaner and it is more understandable. Okay. Now, what about this H of I right here? See, this term is very easy. This term is just a regularization term. It is remaining the same. Okay. This half is fine. This ft of x of I square is fine. This is basically the corrections that we were making in the model. Okay. The only new things in this formula are the gi and h of I that we need to figure out as to what they are. So the h of I is a new thing. It is very interesting to understand. H of I is nothing but the double derivative of the loss function with respect to y hat. Okay. Don't worry, I will be explaining it. And since this is called as the gradient, the double derivative here also has a name. It is called as the Hessian. The Hessian. Okay. Now, this very important things to discuss as to what do these things mean. Okay, look carefully. So, what is the gradient? Okay, what does the gradient mean? We discussed this. The gradient is basically, something that points in the direction of the loss. Okay, what does that mean? So, we have got something like, let's say this graph right here. And, we have a function that we need to optimize, which means we want to minimize the function. Why? Because it is the loss function. We want to minimize the loss function. So we calculate the slope at different points, at this point, at this point, at this point, at this point. Okay, this is how the slope will look like at different points. Okay, this, then here it will look like this. Okay, and whatever is the direction of the steepest slope, that is the direction, that we take, that this is the direction where the loss increases the most, and hence we go to the opposite of that. That is how, basically the gradient boosting algorithm works like. That is the intuition of gradient right here. But what about this Hessian? So the Hessian is basically the rate of change of gradient. So you see, at this point, let me mark it as point A right here. So at point A, let's imagine I'm taking out the gradient. Okay. I'm also taking out the gradient at point B. I'm also taking out the gradient at point C, then point D, point E, and so on. Okay. Now, how is the gradient changing? Okay. Like how is the slope changing at each interval? That rate of change of the gradient is called as the Hessian. The Hessian is represented in 3D. It basically represents the curvature of the model, and the gradient basically represents the slope of errors of the model. Okay. So, another way to understand, if you want like an easy example, let's say we have the example of velocity, the same velocity that we studied in physics in class 9, class 11, whatever. So velocity is nothing but rate of change of distance. This is how it looks like. And what is acceleration? Acceleration is nothing but, just a second, sorry. And acceleration, what is acceleration? It is nothing but the rate of change of velocity, right? So when I write this, I can also write it as d by dt, and I can take this value and I can write it in place of v to get ds by dt. Okay. And when I write it completely, this is not multiplication, this is differentiation. So I will get something like the double derivative of s, okay, with respect to v. This is what it looks like. So this is the same intuition that we are having in this case. Okay, this is how the same formula is looking like. The gradient is telling us about the rate of change of the loss. Okay. It is telling us that this is the direction, this is the steepest direction of increase of loss. And the Hessian is telling us that this is how the gradient is changing at every point. So this is represented by 2D, and this Hessian is rather represented by 3D. So just a second, I will go back to the repo to show this to you. I've included a very good comparison. If you go in here, so you see how amazing of a comparison this is. You can read it later. First, come down to this image right here. So this is the 2D representation and this is the 3D representation. Like I said, Hessian is part of the 3D. So if you look carefully, this is the loss function, theta with respect to the loss. Okay. This is our function that we need to optimize, and we calculate the slope at each point. Wherever we get the steepest increase, that is what we consider as a gradient, and we move opposite of that because it's very intuitive to move opposite to the direction of the steepest increase of loss because we are trying to minimize the loss. So let's say that this is what it looks like. Okay. It tells us the direction of loss of increase. Now, when we go on to the Hessian, see, it is represented as a 3D representation. It is a function of loss and two different variables. So this is the curvature. Okay, if this is the curve, like the slope, this is the curvature. When it is represented in 3D, it is called as the curvature. So at each point, how this slope right here that we calculate in the gradient, the way it is changing is called as the Hessian. Okay. So it basically tells us the curvature of the lost surface. Okay. So this is very intuitive to understand. The information that the gradient provides is, where in which direction should we move. It basically provides us with that information. But if we need to understand how aggressively we should move, that is provided by the Hessian. Okay. It is the second derivative, and it is basically used for faster and better convergence. Okay. So now going back to the board, we have got this formula and we have interpreted the values of Gi and H of I respectively. They are basically the gradient and Hessian values, which we calculate in this case. And these are eventually the ones which make XGBoost the strong model that it is. Okay. So let me now go on to the next step, which is pretty important. Okay. So, you know, let me just write it here. So you see, we have got the summation term in here. Okay. This summation is happening here. And we are doing the summation for I from 1 to n. We have got this as the gradient and this as the Hessian. So what we do is we do another small approximation, and what we do is we write the summation of all gradients g of I as capital G, and we write the summation of all Hessians h of I as h. Okay, we can do this because they are just slopes and curvatures, and it is comparatively easier to do a summation for them. So this is what we have done just to, make the formula much more writable and much more interpretable. Okay. So now when we look at our updated formula and we see how it looks like, it will look something like, summation. Okay. G of j multiplied by wj plus half hj into wj squared. Okay. So let me put this right here. Then basically the regularization term. Now we open it up because it is required in the solving. So gamma of t plus half of, need more space, uh, lambda summation wj squared. Okay, simple. Now, while solving, we can see that this term and this term, they are the same denominator, 2 and 2. So these terms can be added. So we are basically now in the process of simplification. So we simplify it, and in the next step, we can write again summation of j, summation of j. Okay, sorry, it's happening here. Okay. Gj, Wj, okay. Then half of Hj plus lambda multiplied by Wj squared and the final term, the gamma term, gamma. Okay. So this is what our final function looks like. Okay. It is still not done, but I'm just boxing it to get an idea as to where we stand. Okay. This is what the final function looks like. So what we have done in this step is that just add these two terms up because they are the same denominator. Take the half and wj square as common outside the brackets and add it all up. Okay. Wait a second. There will be this bracket before the summation. Okay. Correct. Okay. So now we have got this as the objective function. Now one final step remains, which will give us our answer eventually. This is the loss function, right? Now this is a very interpretable loss function. As you know, you can see every term is with respect to wj. You see this wj is coming here, then this wj is coming here as well. So we can now basically go on and take its partial derivative in order to calculate the minimum value of the loss function. So we do that. So, we do something like del of f. F is nothing but this function right here, f, okay. Del of f with respect to nothing but the model weights, which is wj. We calculate this. So we take the derivative for this entire term there along with the gamma t. And doing this, we basically if we look at it, so we are taking the partial derivative. So there's a rule in calculating the partial derivatives. This is a way in which you can solve them very quickly. So in partial derivatives, we can see we are taking the derivative with respect to wj. So every term except the term which is not having wj will be treated as a constant. So when we go here in this term, this wj is fine, but this gj will be treated as a constant. So when we take the derivative here out of this term, we get nothing but gj, okay, plus. Now when we take the derivative of wj square, we get 2 into wj. Okay, this is basic differentiation. We already have the half from here, so we multiply it with the half. I'm writing it like dots to save space. And then hj plus lambda is copied as it is because it is being treated as a constant. Hj plus lambda. Okay. This gamma t goes on to, this gamma t, it basically goes on to zero because, it is a constant. So this is the final equation that we are getting. Now, solving this further, we can get the value of wj. So the value of wj will be nothing but minus of gj divided by hj plus lambda. This will be the value that we were after from such a long time. This is sort of the answer for the model. No, we are not done with the process yet, but this is the answer for the model. This wj is nothing but the individual least weight that we have calculated. Okay. Now, what should we do next? Very simple. We have our equation here that we had right here, if we calculated. So we have got the value for this wj now. Okay, let me take a different color. We've got a value for this wj now. Okay, this wj right here, which was missing from a long time. We just calculated it. So what do? We take the value of wj that we just calculated, this value, and we plug it back into our loss equation. So we plug it back in here. Okay. You can do the math on your own. I don't want to write so much. It is just a few terms will cancel if I do it quickly. You can take a pen and paper and do it alongside as well. It will give you much more clarity. So I have got summation, okay, and I had Vj multiplied by Wj. So in Wj, I can write the value of Wj, which was nothing but minus of Gj divided by Hj plus lambda. Then I had the half. Okay. Then the Hj. Okay. Then I had the Hj plus lambda. So I can write it in there as it is. Hj plus lambda. Okay. Then I had Wj squared. So when I write Wj squared, it is Gj squared divided by Hj plus lambda whole squared. Okay. And then finally, I have the gamma t term, which is as it is. No one can do anything to it. Okay. So now this will get cancelled with this, and Hj plus lambda will be remaining in the denominator. Okay. Uh, this will stay as it is, this one right here. Okay. And now we can see this denominator and this denominator is now the same except for this half. So we can take the LCM. You can use the LCM method here to get to the final result. So when we solve it eventually, we get to the final answer that we were after for such a long time. This is it. Okay. Minus half summation Gj squared divided by Hj plus lambda plus gamma t. Okay. This is it, guys. Ooh, finally. This is eventually our answer. Okay. We'll obviously have to discuss what this means, how is it helping our model, and all of these things. But this is the final mathematical solution that we get at. Okay. The final one. So this is basically called as the quality score of the tree. We use it to analyze which gains should we keep and which gains should we, ignore. That is how it happens. So this is what we get. So now, to make it much more interpretable, I'll just write it in another form. So you see this sigma right here. It basically means the summation because this is the collective formula. This is the formula for the entire tree and all the leaves. If I do it for just one individual tree, what will it look like? It will look like the left node, the right node, and the parent node. Okay, like if I take a very simple tree like this, how will the formula change? This summation will be removed, and you can basically write it as gain that we calculated. Just a second. Okay, gain we just calculated is equals to half GL squared divided by HL plus lambda plus GR squared divided by HR plus lambda, more space, minus GL plus GR whole squared divided by HL plus HR plus lambda. Okay. And outside the bracket, we write our typical stuff, gamma. We don't write the t. Why? Because we are evaluating for a single tree. So for a single tree, we know what the number of leaves will be, which is why we don't write the t. Complete the bracket here. And, if I want to write the whole thing in a box, it is not fitting on the page. I can write it like this. Uh, Minus of gamma. So this is what we get as the gain value finally, and this is for like a single tree. I've written it this way because it is much more interpretable. I'll tell you why. So this L here means nothing but left, and R here means nothing but right. Because if we look at the single tree type of example, we only have like two nodes. This is the left and this is the right. Okay. So basically, this is the formula that we get in the end. This is what the model is running on. What we are saying to the model is that, okay, you calculate the value for the left node, for the right node, and then for the total. Okay, you calculate this. We're calculating this entire value right here. Okay, this value. And what we are saying is this value will come out to be, let's say, some value x, whatever value. And this gamma eventually will decide whether the split that we created right here, the split for which we have the value x, whether this is worth keeping or not. How does it decide that? So when the split value x is greater than gamma, it means that the split is worth keeping. It means that, the model complexity that is being added, it is fine. You can keep it. But if this x is less than gamma, then it makes no sense to keep the split and this split will be rejected. Okay. This is how the entirety of XGBoost works like. Okay. Now, let me tell you the intuition. We already discussed gradients and Hessians. So, we know this capital HL is nothing but, the summation of all the Hessians for the left node, and this GL is nothing but the summation of all the gradients for the left node. So, the gradient, as I said, I circle it in order to make it clear. Like I said, the gradient is representing nothing but the slope of the loss function, the direction in which we want to move. Okay. And by how much should we move in that direction? How aggressively should we move in that direction is decided by the Hessian right here. Okay. To prevent overfitting so that we don't, move too fast. We don't memorize the noise within the model. We have added the regularization parameter, which is part of the L2 regularization, which is in the denominator lambda. So you see how everything makes sense now. The left tree is mathematically pruned. If it is, prone to overfitting, this lambda value is in the denominator. So it will reduce the value of this entire term here. Okay. And that will eventually prevent overfitting. Okay. If we are going to the right one, we have the same parameters here. So this lambda in the denominator will reduce the value of this entire term, which will prevent the overfitting that we wanted to prevent in the beginning. Okay. This basically, if you still want to interpret it more, if you have large gradients and, you have a smaller value of lambda and a smaller value of Hessians, it gives you a comparatively better model to use. Okay. So this model learns very fast. It is generalizable. It is super duper interpretable. Okay. It deploys very efficiently. And the tree, the main thing, the tree is mathematically pruned due to this lambda parameter of the L2 regularization. Okay. This is, there is a reason this is so strong. This is combining gradients, this is combining Hessians, and it is combining regularization. And, and it is also checking the tree complexity and the split trade-off using this gamma parameter. So all bases are covered. Okay. XGBoost, it is based on, gradient descent, stochastic sampling, and Newtonian optimization. This method of, optimizing the function is called as the Newtonian method. So this is why the XGBoost is so strong. Okay. So now everything is, extremely clear to you. You have got why we are using the gradients and the Hessians, why these equations come, how the Taylor approximation is happening. If you want to understand the Taylor approximation and specifically how it was used in here, I have attached an article in the description. You can read and check it out. Okay. And, if we move forward, let me check if anything is left. Okay. So, it is just the most important thing is in here is to understand the three things that we have got, which is, if I need to write this down, it is pretty important. The three things to understand are what are gradients doing here, okay, which we understood in the gradient boosting as well, so it's not something new. What are Hessians doing in here? Okay. And eventually, the last thing, what are the hyperparameters gamma and lambda doing? If you understand these four things, your job is essentially complete because, If you understand these four things, that will give you an idea as to how the model is working. Rest of the stuff is just mathematical calculations. So the gradient, sorry, so the gradient gives me it gives me the direction of the error, okay, which is important because we need to know the direction of the error in order to move away from it. The Hessian tells us how aggressively you should move away from it. Okay, what is the confidence value in that direction? That is what the Hessian is giving us. Why? Because the Hessian is the double derivative of the loss. It is the derivative of the gradient. Okay. This is basically, the parameter, the gamma parameter that we use to determine the split. We are basically asking, whether this split is worth keeping or not, because it is adding complexity, which is fine, but it is only fine if it is worth keeping. So, gain values which are only greater than, if I write it, gain calculated, if the gain values calculated are, what is this? It's not this symbol. Sorry, guys. So if the gain value which is calculated is greater than gamma, then and only then we keep the gain. Otherwise, the split is rejected and we go for some other split. Okay. So this is like the quality control parameter. And this right here, lambda, this is nothing but the L2 regularization parameter. And if you want to know about L2 regularization in depth, I have put another article in the description. It is very easy to understand. L2 regularization, it just, it punishes the very large values, and it basically leads to a much more interpretable model. So these are the four, parameters on which the entirety of XGBoost is based. And this is the entire model mathematics. I tried to understand, I tried to explain it as intuitively as I can, step by step, so that nothing seems like a black box, nothing seems mucked up. Okay, it's all clear and it's all mathematical. Okay. Now, moving on to the model stuff, which we now need to discuss. It's basically about the model hyperparameters. So if I go back to the repo, and I start moving. So you can read this. I will not be covering this. This is the same thing that I explained on the blackboard itself. Okay. This is the formula for the XGBoost trees. This is how, uh, this is nothing but the correction function that we get in the boosting. Okay. This is the regularization objective. This is the same formula that we derived. They have just, in the repo, it's just opened up. So, this, if I show it to you, this function, we derived it. Let me quickly scroll up. This is the same function. This is right here. This one. We just derived it, and then the ohm of ft. Okay, so we did derive everything. The symbols are explained. You can see what each of the thing means. So if someone has not watched the video, they can understand quite a lot of stuff by reading the repo as well. All of the theory in the repo is it's very intuitive, so that it doesn't seem bookish or mugged up. You can understand it. This is how changing gamma and changing lambda, basically affects your model. So it is for the L2 regularization. I covered this entirety. Okay. And again, this combination means that XGBoost optimizes jointly to fit the data, as well as, the simplicity of the model, which the model on day 8, the vanilla gradient boosting does not cover. This is how the second order Taylor approximation works. Okay. This is the first derivative, the gradient, second one, the Hessian. I just explained it. The final loss function that we derived, you can check all of this out. This is easy. Okay. This is something that we should discuss. It's pretty easy. So, we take this to group all of the gradients and group all of the Hessians. This is the summation. So, let me jog your memory pretty quick. We did it right here. Okay. Where did we go? Yeah, right here we did it. Okay, so this is the same thing. So it explains that if the gradient values are very high, very, very high, it means the model is wrong in this region. Why? Because the gradient points to the loss. So if the gradient is too high, it means the loss is very high in that direction. Okay, this is simple. And if it's a large Hessian, it means that the region is very stable and confident, because a large Hessian value means that the rate of change of gradients is very high. The curvature is large. Okay. Small Hessian, it means there's a lot of uncertainty and we should be very cautious operating in that region. This is the leaf weight that we derived, WJ. Okay. So this is, I explained this, this lambda right here, it will regularize and mathematically prune our tree automatically. And Hessians are divided because the larger the Hessian value, the better the model is. And GJ again, gradient values. If the gradient values are large, the model is wrong in that region. Okay. So this is how the weight is intuitively updated. This is the tree quality score, the final formula that we derived in the end. This is the tree gain formula for a single node, left and right, both. This is the same thing that we derived. Very important. You can look at it, gradient versus Hessian. This is all theory that we have discussed. This visual representation is the most important. Like if you want to fit this in your mind, you cannot memorize the math. You cannot even memorize the code or whatever. What you need to take away from these things are the concepts involved. Okay, as they are repeated. Okay, this XGBoost, when you just write XGBoost regressor, you are writing a normal Python function, but in the back end, it is working based on all of this math. The entirety of AI, it is based on math, linear algebra, statistics, probability, differential functions, integral calculus, differential calculus. It is all based on that. So, the better grip, the stronger grip you have on those concepts, the better understanding and the more sound understanding you are going to have for all these concepts. Okay. So this is it right here. Gives the direction. We have discussed this. You can read it as well. The significance of. I have again tried to cover this again and again because this is the part which sounds most confusing. As to what role are the gradients and Hessians playing. So there is another analogy you can see. The gradient answers where we are wrong. The Hessian answers how aggressively should we correct, and the gain answers is this split even worth making. Okay. These are the key hyperparameters. So since this is using a tree-based model, the hyperparameters are what the tree-based models have. So in estimators, it is the number of boosting rounds. You can see how it increasing it changes the model. Learning rate, again, we give some sort of a naive value, and then we can take a set of logical values and let grid search CV decide which value is the best. Max depth, gamma and lambda, these are the new parameters that we discussed today. Subsample is the fraction of rows for each tree. So this basically it allows randomness into the model and it basically ensures that a different subset of the features are taken. It reduces the variance in the model as well, thereby preventing overfitting. Okay. So again, like I said, how we move in machine learning in a standard way, we never go for the best model at once. We first build some sort of a baseline in order to compare. So this is like, if we are giving a data structures and algorithms interview, even if you know the most optimal solution, you first give the brute force, then the better, then the optimal, because that is the way how you build up. Okay, from basically your baseline models to your best models. So you'll take your, let me just clarify it. You take your baseline first, and then you sort of tune it or optimize it. Okay, so that is what we have done here. Gradient boosting was the first baseline that we built yesterday. And then we chose the XGBoost. So for the XGBoost as well, we chose a baseline. So for the baseline, we took some parameters. Now let me open the code. So these are the XGBoost regressor. Okay. So these are our parameters. These are all parameters which are added by us manually for the baseline. Okay, these are values that are intuitive, normal, logical values, and these basically create a baseline model using which we can analyze the performance of our future models. So this is all normal values that we have given. N jobs is equal to -1 assigns the number of processors to this task. When we write -1, it means the process or the model running can use as many as it wants. Random state is equal to 42 gives us reproducible results. We have taken gamma as 0 just to do it. Okay. This is how we fit the model. We also calculate the training time and the inference latency. So you can check it out. This is the root mean square error since this is a prediction problem. R2 score and root mean square error make the most sense. Okay. Now we do the tuning. So, how you can see how we took singular values here. For the tuning, we give a set of values. So two here, three, three, two, 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 and two. If you multiply that, we are getting 2 into 3, 6, 6 into 3, 18, 18 into 2, 36. 36 into 2 into 2 into 2. So 36 into 8. So if I write it, 36 into 8, I get this value right here. So these are the number of combinations my model will be running. Okay, wait. 36 into 8, 8 into, wait a second, this is my calculation, correct? Yeah, that is correct. Okay, so these are the number of combinations that the model will be running. Okay, this is important to analyze because when we look at the training time between the tuned model and the baseline, the training takes a significantly larger time. Okay, this is how we train the grid search CV. Okay, uh, this is the inference latency and prediction time. We compare the results for the tuned and the baseline models. And if I open up the results, this is what they look like. So you see 69 seconds are taken for the tuned model, whereas the baseline takes like 0.62. So this is the difference because the baseline is running one combination of all the hyperparameters, whereas the tuned is running 288 combinations. Why? Because we have given a lot of hyperparameter values to select from. This is the inference latency. The R2 score, obviously, it is a bit higher for the tuned model as the tuned model gives us the best results. Root mean square error is a bit low, which basically means that this model is still pretty interpretable. Okay. We print the best set of parameters available. So these are the best parameters. So basically, when we run these 288 combinations in the grid search CV, we then ask the model using grid.bestparams, this one, to get the best parameters in our model. Basically, which combination of these parameters is the best one for the model. So the model gives us these set of values of this. This is always good to print because it gives you an idea what your current best model is. You can check out these visualizations. These are common from the old ones. This is the prediction error. Okay. Feature importance again, being a smoker or not is the number one feature which helps us predict the insurance charges. Okay, this is the boosting error visualization. So as we know that training and testing error, the closer it is to each other, the better a model is considered because if the errors have a huge difference, it will definitely point to either overfitting or underfitting. We don't want that. Okay. So this is it for the visualization part. If I get back to the repo, you can, by the way, read all of this. This is nothing but the metrics analyzed. I have just wrote it down in a much more intuitive way. Okay. Boosting stage error. This is the analysis. The same. Let's move forward. Okay. Looking at the time complexity, it looks the same way that we analyzed. So we have got C combinations, which means we have got 288 combinations. Since it is a tree-based model, the complexity is still T for T trees multiplied by n log n for each of the tree. Why it is n log n? Because whatever way we create the split in the tree, n log n is used to sort. So whenever we sort and we do a best form of sorting, we get the time complexity as n log n. P is the number of trees. We have done a cross validation using k folds. K is nothing but 5. And then we are running a total of 288 combinations for the hyperparameter. So multiplied by 288 again. Okay. This is the value that we are getting eventually. So T3 is n log n for the sorting, 5 for the cross validation, and 288 for the combination of hyperparameters. Okay. This is the value that we get. So, don't analyze your time complexity in a naive way. Deep dive into it, open it in its entirety to study it. Okay. Prediction is simple. It will just be for the real time inference. Okay. Space complexity, we discussed this. This is the same as the gradient boost one. So for this, we just need to understand as to what the model is storing. So, a tree-based model stores all of the nodes in the tree. And the maximum number of nodes in a tree, we sort that as 2 to the power d because the nodes scale as a power of 2. This is simple. Now, the final thing, which is pretty important, the failure cases. So, XGBoost is still a very strong model, but it still has its own failures. So, noisy or mislabeled data. Now, this is the headache of a data scientist right here. If your data is noisy, if there are too many outlier values, the model will not train well. No model is like a magical solution to everything. Your data needs to be clean because all models are eventually based on the data itself. If your model is not clean enough, the data, you know, if your data is not clean enough, your model cannot do anything. So we need to do this subsampling. We have done the subsampling using these two parameters. Partially, we fix the problem, but noisy data problem still remains, which is why the data preprocessing pipeline is very important here. Then extreme expense outliers. So, we have got some individuals which are very high cost individuals. So these are outlier values which lie very far away from the average values or the mean. So these cases, they basically harm the model, hamper the model, they delay the convergence in the model, and basically give us a model which is not as generalizable. Because we cannot always predict extreme values using gradients. Gradients usually predict average values. Okay, so this is it. Extrapolation, this is very important. If you predict something which is not a part of the existing data set, then the model produces unreliable estimates with no uncertainty signal. So tree-based models cannot extrapolate really. They can only interpolate with the feature space. So this is still an issue in this. Okay. High dimensional sparse feature spaces. This is a new problem. I don't think it was covered in the gradient boosting. So, as we know, XGBoost performs very well when there are the large non-linear relationships in the form of a tabular data, which means a structured tabular data. But the thing is, when the model dimensionality, when the data dimensionality, pardon, where it increases too much, which means that the number of features scale to be very high, in those cases, tree models struggle to find good splits efficiently. So eventually, the model might fail. Okay. So for those cases, we have to try and go for a deep learning approaches, which I have talked about in this next section as well. So you get tabular data, non-linear relationships, and data does not have a very high dimensionality. You can just close your eyes and straight away bet everything on an XGBoost model. Okay, anything which has like a low to medium or a medium high, let's say medium high sort of a data set, not a very high or a very large data set, it will be trained very efficiently with good results using an XGBoost model. If it exceeds 10 million samples, dimensionality is very high. In those cases, we will have to go for a neural network based solution. Okay. So this is it covered everything for the XGBoost. Okay. So I have attached a few articles for different things in the description. You can check them out separately as well. And just before going forward, I just wanted to say something. So if you didn't understand any part of it, or if you didn't understand some parts of it, it's fine. So you should just spend a little bit more time on it. Just go through the video once again, read of the articles. Because, this stuff that we are doing here, this is not easy to do. Okay. I mean, there exists a lot more complicated concepts as well, but this is still pretty complicated. All of the math, all of the intuition, everything. And you do need to memorize the important things as well. What I'm saying is that, don't take your understanding of these things as for granted. They are not easy to understand. If you understand even certain things, you should be happy about it. And you should always strive to understand better things. Okay. This understanding, whatever you understood today, take it as a privilege, not as a like a for granted thing. Because it takes a lot of commitment and a lot of focus to understand this math and then try and implement it from scratch. So just keep, maybe you can take a pen and paper, try out the calculation on your own again, and it will make sense because it is all in front of you. There is nothing hidden or nothing confusing in here. Okay, it is all done in front of you in like the cleanest manner possible. Okay, so do check out the calculations. They will make everything clear. I will attach the link to the code and the GitHub repo in the description as well. You are welcome to check it out. This is the data set. It is the same data set from day 8. And yeah, I think with that, we conclude day 9. And I will see you tomorrow on day 10 with, let's see what we have. Rossman's store sales forecasting model with a light gradient boosting model. So this is very interesting to build as well. And I will see you for now.